Hello everyone, welcome to today's Software Developer Thursday. Today Francesco Corcoglioniti of University of Bolzano will present us how accessing web APIs as virtual relational database or knowledge graph. I won't steal him more time and I pass the microphone to him, so the stage is yours.
Okay. Thank you everybody for coming here, and thank you for Noe to host me in this event. So, I would start with this slide to tell you a few words about who I am. So I am a postdoc in UNIBZ. I work in the group of Diego Calvanese. So we work on applying semantics to data management. I'm also working with some projects, and in some of them I work together with Ontopic Srl, which is a former startup here. Now it's a full company working on semantic technology and ontology-based data access. So these guys are also supported. And I was supported by HIVE, which was a Fusion Grand project that just ended recently, which is behind this work I'm going to tell you about. Now, as I said, in my group, in our research activities and in our project activities, we deal with data management using semantic. So here I put some keywords, buzzwords that you might have heard, like relational databases, ontologies, knowledge graphs, RDF graphs, virtual knowledge graphs, which we can build on top of relational databases, and so on and so forth. Now, a common thing among this stuff is that we can leverage established query languages that are very flexible. They allow you to do a lot of stuff. Here I mentioned two of them, maybe the main tools we are dealing with, SQL and SPARQL. So we work on these languages, and many of our projects deal with them. However, what we notice from our little perspective is that most data nowadays is available through web APIs, so I'm not telling you something new, but it's something that has to be accounted for. So you deal with the APIs when you have to deal with third-party data, because typically you don't have access to the database of the guys, you go to an API. You deal with APIs, for instance, to access real-time data, because you need to get fresh data. You might need to deal with APIs to access services that are related to data. So if I have to do some kind of text search over my textual contents, maybe I go to an API instead of going to, let's say, a query in SQL or SPARQL. So somehow it's a need for everybody to deal with these APIs. Now, I reported some statistics here about how APIs are widespread. Again, I don't think I have to motivate this further. Maybe one thing that captures my attention is that 83% of all the internet traffic is due to APIs, 90% of developers use them, and 30% of developers' time is spent on coding APIs, both on the server side and on the client side. Now, I don't have the clear distinction, but surely if you can help people accessing APIs, I'm mostly dealing with the client side here, not how to build an API, but how to use it. So if we can help people using APIs, for sure we are hopefully reducing this 30% of time that is wasted like this. So, what we want to do in one slide. So, starting from the motivation that for databases, for knowledge graphs, we have simple ways to access them, SPARQL, SQL. We would like to do something similar on top of APIs, or, well, also involving data from APIs. So here I put two pictures showing you the relational case, here on the left, and the knowledge graph case on the right. And the idea is to give our users, or to give ourselves, if we are the developers, an abstraction of a unified relational schema or an abstraction of a unified knowledge graph, whose data, however, resides in different sources, APIs, or let's say standard relational database, or well, I wrote RDB source, but could be a standard knowledge graph on the right side. So what does it mean? It means that we have to do a kind of integration, solve a data integration problem to provide this unified abstraction. But we want to do it in a virtual setting So the data is not copied to a single location, so we are not doing ETL, extract, transform, reload, but instead what we are doing is more like a data federation. So we receive the queries, the comments that come from the client, and then we split them among subqueries that go to the single sources, and among them API calls that go to the API, in order to orchestrate these different sources and answer our user query. Now, as I said, we started tackling this issue from the point of view of inside the HIVE project, which was a full concurrent project, and we are continuing this work now with different perspectives. So, also to start with, because I will go back on this in the demo, here is just an example scenario. This is taken from one of the use cases we have in the HIVE project. So, let's say, as an example of using an API together with the relational data, what we want to do is to extend the Open Data Hub dataset, and here could be the relational database, but also the knowledge graph that was built on top of this relational database, to extend it with semantic search functionalities. So, as I wrote quickly on the corner, semantic search is a form of text search where we are not just looking at exact term matching, but we also try to capture the overall meaning of the text using, let's say, techniques that come from the natural language processing. So usually, for instance, in this example service that we implemented for this use case of HIVE, we used a model-based operator. But this is not about the topic of today. This is something else. Let's say we have this nice API we want to use so that users can answer queries like the one I reported here. So I want accommodations in South Tyrol that should have certain features. For instance, I want at least the rating to be 3 stars. So notice here I'm dealing with a structured constraint, so I'm predicating over some structured field of this item. And I want also, in general, the text describing this accommodation to match a search string, which in this case is horse riding, could be nice panorama, could be whatever I may come up with. So I want also to match this in the text. And I mean, if I have to use just the features that SQL and SPARQL give me, maybe I should have to do regex search or use some proprietary extension of knowledge graphs. Here I'm integrating a separate API to do that. But really, this is just an example. For instance, we have another use case which, however, involves private data, where we are dealing with weather data coming in real time. But since part of the data is not public, I cannot show you a demo of that. So let's stick to this. Now, as I said, I'm tackling both perspectives. So accessing APIs within a relational setting, accessing APIs within the knowledge graph settings. Of course, I started from the second one, the knowledge graph settings, because it's what I've done in the project and what is my focus. But in order to reach that goal, I was passing through the relational setting. So, and I think also the results we developed tackle both of them. So, a little background on APIs in the relational setting. So, it's not something new. So, there is quite a literature about that, and there are, I think, 2 streams that are somehow related to this. So, as I mentioned before, there is the whole topic of data federation, because when I access an API, usually I don't access an API in isolation, but I do that by integrating data from the API with data that comes from other sources, mainly relational database. So I'm mostly, very often, I'm integrating data from multiple sources that are independent, they are autonomous. So this brings me to the scenario of data federation and the problem which is federated query answering. So taking a query over the unified schema and dividing it in subqueries over the individual sources. And this unified schema, sometimes in some products, I mean, is known also as virtual database, virtual because, again, we do not move the data stays where it is. And there are many proprietary and open source data federation systems. I mentioned one of them, cont'd, which is the one we worked with in our, let's say, project HIVE. It comes from the guys that, from Red Hat, the guys behind JBoss. but there are many of them. The second stream of works related to query answering under access pattern restrictions. And this is the key to understand a bit how to use APIs in a relational setting. So first of all, we consider tables that can be accessed only by specifying, constraining some attributes. So imagine a table about temperature observations about a city. I can read the observations of a specific city only, so I cannot read all the observations. You have to provide an input to one city, and then I read the temperature observations for that city. So there is one attribute of the table that I must constrain. So imagine a query, select temperature from my table where city equal to something. If I do not put city equal to something, no way I can access it. And you can imagine that this is very close to an API having some inputs. If you do not provide the required inputs to an API operation, you do not get any output at all. So you cannot invoke the operation. This for required inputs, that you can have the optional ones, so the situation is more complex, of course. So as I was saying, API operations, we can see them as access pattern restrictions over a table. The input attributes are the columns of the table that I must supply. The output attributes are the columns, I don't know, that I can obtain. Technical support, please. Okay, now it's working again. Sorry. I was temporarily disconnected. Now, in the database literature, there is this focus about solving this problem. So given a query, in this case an SQL query, a relational algebra query, find a query plan that is a low-cost plan, so there should be some optimization matrix, so on and so forth, that satisfies all these access pattern restrictions and allow us to answer the query. Now, there is a lot of research on this, taking into consideration also other phenomena like the pagination of web APIs, the fact that you might have limits, so you can get just, let's say, 100 rows and that's it. So, and then you wonder, will I get the complete answers to my query or not? So there are several problems that are addressed there. Now, my focus to start with was mainly practical, so I started from, let's say, the basic problem. Can I implement this? Can I find solutions to do this and to bring it into my knowledge graph setting? And well, the answer is yes, because there are indeed some systems that support some of these operations, but the support is somehow limited. So there is something, for instance, in TED for OpenAPI APIs, but many features are not there yet. So you can find something. What we have done in HIVE goes maybe a step further, but I mean, there are several attempts to implement this. Now, moving from the background, the problem, towards the solution, here is how we start dealing with the problem in the software we developed. But keep in mind that what I'm telling you is not just our specific solutions, but I'm also mentioning several open source products that you can use independently from what we have done. So every time I mention TED, this is taken from TED, is a configuration of TED. You can use it as you can use our solution because it's open source. Now, the first problem that you have to address is to define this virtual database where some tables are mapped to API operation. Now, there is a standardized SQL extension, which is known as SQL-MED, which allows you to do that. And here I reported an example of what you have to do. So you create your virtual database, HIVE ODH, because ODH is the use case of GitHub. Then you say, I have one source, which is of type Postgres, so the wrapper is of type Postgres, and this DB source provides me a schema that I call DB. Then I have another source, which is of type service. This service is our extension to access APIs, which has another schema SRV. For the Postgres source, easy, I can import all the objects of the source, so all the table definitions, the procedures, so on and so forth. I can import them easily because the source is a database, is Postgres, so the tool allows me to do this kind of import. For the API source, SRV, instead, I will do a bunch of definitions that I will tell you about later. But at the end of all this operation, I will end up with a database having inside the two schemas, one for the relational source, one for the API source, and I can write queries addressing both of them. And there could be many other sources here if I want. Now, the solution we devised in HIVE for doing that is the one of introducing these API bindings as a way to bridge the API and the relational world. So API bindings are a set of create foreign procedure, which is a standard statement in SQL MED, or create foreign table statements that build a relational view, so a view in terms of tables, over my API methods. So to start with, what we do is that we interpret each API procedure as API operation, as an SQL procedure. So SQL procedure like the one I reported on the right. Procedure, they take an input tuple and they output 0 or more tuple. So these are so-called table procedures. And here you can see I have API semantic search query, which takes a query as the input attribute and returns tuples with this for attribute, the query itself, and then the identifier of, in this case, the accommodation that I matched, the score of the text search, and an excerpt that tells me which piece of text was matching exactly my query. This part is standard. The options are our extension. And they serve basically to do the binding, because if you look at the options, you see I'm saying the URL to call in order to implement this procedure is this one. The method you have to use is HTTP post. The request body is that one, so it's a JSON object with some placeholders, so the query placeholder, the query must be injected there. And the response body is what is an object which with a matches attribute, which is an array in JSON, and it's an array of objects, each having an ID, a score, and a result. So I'm telling the implementation that we made how to parse the response back into tuples of this with these attributes. And well, this is a simple template language. Then we have also more elaborate solutions for doing that. Just you need to provide this kind of binding. Now, this was the first step. The second step is the one of saying, okay, now I have a bunch of API operations, and they all deal, or they deal with the same kind of data, which I model as a table. So I say a table, which I call virtual because it doesn't exist in my database. It's in my mind, and then I use it in order to answer queries. A virtual table is defined in terms of attributes, and it is linked to one or more API operations, so the procedures. You can see it here, an example. You have a table which has the same attribute as I said before, the query, the identifier, the score, the except, and it is linked to an API operation with the role of select. So select tells me, use this API operation, which was the SQL procedure I told you before, in order to extract select data from the table. Below there is another example. Here I have a table that models the index, the full text index, which has just two attributes, the identifier and the text. And I have two operations of the API, one for doing upsert, so insert or update tuples in this table, and another one to do delete, so delete the data from the table. So basically the intuition, the idea is I define a virtual table and then I link it to multiple API operations with different roles. Operations to select data, and there can be more than one. Operations to modify the data, operations to delete the data. Now, keep in mind, our focus is mostly on querying data, so select are the most important. But in the whole picture, there are also the operations to modify the data, and I will show you in the example why they are. So, how we implement then query answering given this virtual database? So, let's go one step back. Now, what we have is this file, which is a VDB file, with a bunch of create foreign table and create foreign procedure statements that I showed you before. Now, the system now has all the information because, sorry, There are also the connection options for reaching the database and all the other parameters that I'm not showing you. So the system has all the information in order to answer a query. Now, we do not start from scratch, but we start from the query engine of TAID. And the query engine of TAID, which is kind of stereotypical in terms of the query engines of the data federation systems, works like this. So it takes an SQL query input, and then it starts looking at the table. So each table comes from a source. Some tables are real tables from the database. Other tables are virtual tables because they come from the API. And each source is associated to a so-called translator or a wrapper. So basically a piece of software that is responsible for accessing the data in those tables. TAID will ask each translator, so imagine this translator as a plugin that you plug into the TAID engine. TAID will ask the translator, what are you able to do? And the translator, in case of, for instance, of the database, it will say, I can do everything, I can do joins, I can do aggregations, whatever. In our case, the translator that wraps an API, it will be somehow more limited because it will say, look, I can just answer single table queries, so don't ask me to do a join, I won't. I can handle projection, filtering, sorting, and slicing, so slicing is limit. And I also impose you some access pattern restrictions in the sense that you are not free to send me all select from where queries for that table, but you must, let's say, provide me some attributes input. So you have to provide something in the where clause so that I can match it to one of the API operations I have available for that query, for that table. Okay, once this is done, TAID knows what it can do for the different tables. So it will use this information about the capabilities of the translators plus some cost heuristics in order to split our SQL query into some queries, each one being sent to the respective translator to be answered. Now, the situation is a bit more complex in the sense that maybe a translator will get multiple queries depending on how the joins are performed. So it's quite a complex issue, this one, but from the point of view of who is implementing the translator, you will receive a query if you are able to answer this query, which in our case is a single table query, which will map to the API, then we are set. And of course, there are parts of the original query that you cannot delegate to the sources, to the translators. So these parts, like the federated joins, they are the responsibility of the TAID engine, the data federator itself. So this is the overall picture, okay? And I mean, you can keep it in mind because it's not so difficult to write a translator for TAID. So you may, if you have a particular source, you may also play with that, and it's quite funny to do this kind of implementation. Now, here is an example of what I was saying before. So here we have a query. It's a query that it's joining accommodations with a semantic search. So what it does, it says, give me all the matches of a search where the query is horse riding. For this matching, I want to find the corresponding accommodation tuples in the accommodation tables, which have the same identifier. So I'm doing the join, and this join is between the two different sources, so it will be a federated join. Now, sort the results by decreasing score, so I want the top matches on top at the beginning. Give me just the first 10 matches. And for these 10 matches, I want the score, an excerpt, the category, the name of the accommodation, the city, so on and so forth. So here I can really pick all the data I like. It comes from the scheme of the Open Data Hub database. Now, TAID will take this query, will run the algorithm I was telling you before, and it will come up with a plan like this one. So it will have two so-called access nodes. These are the subqueries. You see there is one subquery, this one on the right, that goes to the database. From the table via accommodations open, extract these attributes. There is another subqueries that goes to this other table, VT sem search match, which I will implement by calling the API. that will constrain the input query being equal to horse riding. So this is the access pattern restriction I was telling you about, and it will extract this attribute. And then the rest is normal relational algebra. So there is a join, a projection, a sorting, a slicing, as limit node. Okay. Now, this is the part of the picture, the most of the picture. However, the picture is not complete because I have one problem. I have the problem that some API operations cannot be invoked at query time. Why? Because they are too expensive. So, I mean, I can try, but maybe my user will wait, let's say, for 1 hour in order to get the results, or for several minutes. Or these are operations that are instrumental for using some API. For instance, if I run this query before that finds the matches to my query using the semantic search API, well, before I need to populate a semantic search index. And in order to do that, well, I can do it separately, so no problem at all. Or if I take the more general situation where the database is changing, so every time the database changes, I want to update the index, then I have to call some API operations that will populate and update that index. So I also have this problem as part of the big picture. So what I have to do now, basically, is to materialize, to pre-compute offline these pre-invoke offline these API operations and materialize some data. Okay. Well, there are several ways to do that, at least 2 ways. So there are materialized views. I can look at the complex part of my query, the one that I cannot do online, as a view that I want to materialize. And if I can do that, then there is support in the data federation system. So TAID will give you the abstraction of materialized views, and then TAID will be in charge of handling it. If not, well, because we needed something more also, if not, we built a small materialization engine as part of HIVE, which allows you to apply materialization rules that are rules that take data from some table and then possibly calling some API that will populate other tables, which are so-called computed tables because their content derives from some operation starting from data that comes elsewhere. So, for instance, here is the rule for materializing, populating the full text index. So, I'm querying the accommodation table. I want the tuples of this accommodations table to have an English description because my semantic search API works only in English. I take the identifier and the text, and then with this identifier text pairs, I will write to the semantic search index table. And this will cause, by virtue of this absurd statement here, the invocation of this API operation that will populate the semantic search engine index. But from my point of view, I'm just dealing with SQL expressions, and the fact that APIs are called to query data and to write data is mostly transparent to me. Well, I have to know it maybe when I set up the bindings, but after that, I'm just working in a relational setting. Okay. Then, this is just a bit of details about how we implemented this materialization engine. You may imagine that there are multiple rules. Each rule may read from one or more tables and write to one table. So here I have rule 1, reads from this table, do something, writes to this table. Rule 3 reads from 2 tables, writes to another table. Now, if you put all of them together, you get a graph of rule dependencies. And then starting from this graph, you can somehow sort all your rules and then come up with an execution plan that tells you, look, I have to evaluate R1 and R2 first. Then, since R3 and R4 depends on data that comes from R2, I will call them later. There is a dependency between the two, so you have to do a fixed point evaluation. After that, I can do R5 and later. Okay, this is just a simple way we implemented this thing. But really, here we can do much more because here we are entering also the domain of change data capture if you want to catch the changes in our source tables in real time. So really, there is more that we can do. Okay, to close this part about the relational world, which is also instrumental to the logical world, just a couple of optimizations that have quite a substantial impact on the performances. So the first one regards the push down, so-called, of basic operations like projection, filtering, sorting, and slicing. Now, the point is, many API operations, they do support this kind of basic operators. Think about an API where you can add a query parameter saying, I want the temperature observation where the city is equal to Bolzano. Okay, so this is filtering. Or I want just the temperature, I don't want the atmospheric pressure. This is projection. Sorting, I want them sorted by time. Okay, slicing, I want just the last 10. So if you have an API operation that supports this kind of basic operators, relational operators, then it makes a lot of sense for you to map these capabilities and use them in answering your queries, because you are pushing down, offloading part of the load to the API. So we do that how? By extending the API bindings with some special attributes that say, for instance, that allows, for instance, to say how to supply the sort attributes, how to supply the limit, how to supply the offset, and so on and so forth. Here there is an example. Now the example is complex. Maybe this part in blue is about a more complex way of do the mapping of the URL and the response body. So sometimes what you get back from the API is a complex JSON, so you cannot work with the simple patterns I've shown you before, but you need really to write some code. And here we are using a library which is called GSTL. It's a templating library for JSON that allows you to generate a JSON starting from some attributes and do the other way, basically. What you see here instead is the addition of these special attributes in red that are the attributes that I can use for saying, constraining the minimum value and the maximum value of this valid date. So this is an API operation for getting indeed temperature observations, and the limit for saying how much of this observation I want. And this limit that I can find here, I can find also here in the complex expression that I use for generating the URL. Now, so basically I'm just providing a way to tell the system, if you have constraints on how many tuples you want, you have constraints in the where clause about of type valid date greater than this certain value or less or equal than a certain value, then you can use them by injecting in the URL in a certain position. So the limit is here, max inclusive is there, and min inclusive is here. So this is a bit more complex, but again, it's a way to capture these capabilities and tell the system how these constraints have to be injected to the API, typically in the URL. But here could be also the request body, so we are also dealing with post, so we deal with both scenarios. Now, if we have this capability, then we can offload computation to the API, and this is clearly an optimization. Now, it's a bit tricky how to do that, in the sense that there are complex criteria that you have to check. So, for instance, if my API supports sorting, but I cannot push down to the API also the specific, let's say, well, I cannot exactly implement the desired sorting criteria by sending it to the API, then I cannot use the support of the API. So, for instance, there are tricky cases regarding the handling of null values. So, null values must come first or last in my query. So, it's part of SQL. So, if the user asks you that the query wants nulls at the end, and your API doesn't tell you nulls were put, then you cannot use it. Or maybe the user wants data in decreasing order, but you cannot say to the API, I want decreasing order, because you don't have a ascending or descending that you can map to the API. And then there are many other cases where there are interplays among these constraints, so that sometimes you cannot push down these operations. So you have to be careful, because otherwise you return incorrect results. The second optimization I want to tell you about regards so-called bulk operations. These bulk operations are operations where I call an API method with multiple inputs. So imagine the classical lookup by ID identifier where I supply multiple identifiers, okay? Or write to my full text index where I supply multiple pairs of ID text, let's say tuples, like I'm doing here in this example. If there is this kind of support in the API, again, it makes a lot of sense to use it, because then you might be able to do less API calls, and also if these API calls on the API side involve computation, think about this indexing operation, which is implemented in terms of running a neural network in order to compute the embeddings of the text you sent, because then these embeddings will be compared by cosine similarity to find the closest matches. Okay, if you run this network on 10 inputs instead of a single one, on 10 inputs it's better. It's more efficient, you make better use of your hardware resources like GPUs and CPUs if you're using them. So it makes a lot of sense to capture these operations. And we do that again with some options that tells me that, look, batching is supported, you can batch at most 10 inputs in your query. Then in this case, you see it's a post with a request body, and the body is an array of ID text objects. So here I know how to supply my 10 inputs. So again, there is the need of saying how to supply this bulk inputs to the API. And then also, there might be cases where some input is fixed. So let's say that there is some parameter, the language, for instance. Here there is no language, but I could have the language, and when I call the API, the language, I can specify it just one. So all the 10 inputs that I supply the API must be all in English. So this is the reason behind this batch group by, where I can say you have to split to create your batches by grouping by language. Okay. Once we have these bulk operations, a feature that we may do, for instance, is to use to improve the so-called dependent joins. Now, dependent joins are an algorithm that is used in data federation mostly in order to do federated joins. Now, take this example where I have one table and I'm joining it with another table on these simple constraints. So the attribute A on R must be equal to A on S. Okay. Dependent join works like this. I start from one table, I run a query on this table, select all the possible values of the attribute A from the table R. Once I have all the values of A, let's say A1, A2, whatever, then I can do a query on the table S where I say, give me all the tuples where the join attribute A is in this set of values, because then I know the value. I know that all the values that can match from R are A1, A2, whatever, and then I can supply A1, A2, whatever. And you see here, this is the typical lookup with a batch of identifiers. If I have a way to do a single API call for this, then it's more efficient. And this is exactly how this is done. Okay. Then also, besides the query part, this is relevant also for materialization, but I already told you, if I'm going to insert these identifier text pairs, if I have bulk operation, I can insert a batch of them, not just one. So this is more efficient to use. So this was the relational setting. Now let's move to the knowledge graph setting, where the work is somehow also less mature because we are still working on that, but also somehow more challenging. Now, a bit of background. Now, I think a knowledge graph should be pretty clear, I hope. So here we are mainly dealing with RDF knowledge graphs, where there is an ontology that specifies the terminology, the classes, the properties of that appear in my graph, that describe the individuals in my graph. So there is, in the state of the art, a branch which is about so-called ontology-based data access, where I try to build a knowledge graph starting from sources that are not themselves knowledge graphs. So these are relational databases, for instance. This is a typical case. Now, I work in a group and with a company that work on these technologies because Ontop is being developed here, and we were working with Ontop. And in this ontology-based data access, what we do is we start from a query, which is a query over the knowledge graph, so-called ontological query, SPARQL. And then this query, we rewrite it at the end of some steps into an SQL query, which is the native query we run on the underlying source. We get the answer from the underlying source, which is a table, and then we will bring it back to the expected answer to the original ontological query. From the point of view of the user, there is a knowledge graph that it can query with the knowledge graph language, which is SPARQL, but in the backend, you don't have a storage for knowledge graphs, so a triple store, but what you have is a relational database, or some kind of other source. Okay, now, ontology-based data access is used to create so-called virtual knowledge graphs, because again, the knowledge graph is virtual because the data is in a model form, relational one, for instance, and it has been mostly investigated for relational databases, although there is a generalized framework that provides you some conceptual guidelines to wrap arbitrary kind of sources, but there is a kind of assumption that is you need a native query language to which translate your ontological query. So maybe the language is not SQL. We have a case where the language is the query language of MongoDB. So my colleagues did all this, applied this generalized framework to put a knowledge graph on top of MongoDB. In our case, for web APIs, we don't have a native query language. So again, what we do? Well, our approach is very practical. So we put a data federation system that provides us this query language. It provides us SQL. So this is just the overall idea. So then, of course, when you want to follow this idea, you want to optimize this whole picture. So you want to organize things so that, let's say, you write an SQL query that goes to the data federation system, but it is optimal for that system. So maybe you have to pay attention to how you put the unions, the joins, so on. So we are doing still a research on that, about how to optimize this kind of source. Anyway, this is the picture. This is the overall architecture we did for this scenario, whereas, as you can see, we have the relational sources, but we have the web APIs, and then we took an engine for virtual knowledge graphs, which is Ontop, developed here in Bolzano. We integrated our extensions of TAID, the ones for querying APIs, and then we have a single system that is able to access both kind of sources, relational databases and APIs. Now, I forgot putting the slide in the relational setting. In the relational setting, the architecture is exactly like this. Just remove Ontop and change SPARQL with SQL. Okay. Here, I could have designed an architecture with an additional components, TAID. So Ontop talks to TAID in SQL, and then TAID talks with our extension to databases and APIs. What we have done is to merge Ontop and TAID so that we have a more, let's say, close integration of the two, which is beneficial for performances, which allow us to do something more when we create the query for TAID, and helps also us into the development, because having to deal with the two separated systems is a bit time consuming. So, as I said, this is the overall picture. In this picture, you can see also the materialization engine, which stays on the other side. It takes data from the database and the APIs, and then it puts it back in one of the two, depending on the rules. So this is another component. And then here you have all the pieces of configuration. The API bindings, which are used here for query answering, but they are also used here for the materialization engine. The materialization rules that, of course, go here. And for the VKG, so the Ontop engine, we need also the ontology and the mappings, which goes there. Here is an example of what mappings can look like. for get mappings here, there should be ontology. So the ontology here is a piece of Turtle that tells you what are the classes and the properties of your domain and how they are related. So for instance, here you can see a subclass relation where you say that an accommodation is a place. And so if I do a query, give me all the places, I will get also accommodations by virtue of this semantic relation that is here in the ontology. On the right side, I have the mappings, forget this, the mappings where I say this query on the relational schema. So imagine I have this relational schema that I told you before, where I integrate the physical tables and the virtual tables. This query here, that is a query on the semantic search API. Its result is a table with some attributes, and I map these attributes in a fragment of knowledge graph that is described this way. So it's a set of triples, so assertions, that predicate over an accommodation individual, saying this individual is a match, it answers this query, it is about this resource which has this URI, it has this excerpt, and the score is this one. So here you should be a little familiar about the semantic web world, about RDF, to be familiar really with what is written there. But in that case, I can tell you this is exactly regular, I mean, a plain OBDA mapping as you can find in the on-top system we are using. So it's nothing new here. The only new thing actually is that in the schema that I can access in my source query, the source here, I can also query on top of virtual tables. So these tables that behind have an API operation. So here is another example about how I can write a SPARQL query, a complex one. Now I will not enter into the details because this is the one of the demo. This query is rewritten by OnTop into an SQL query. This SQL query then can be set to tail with our extension, and then you get the answers. And these answers will be the answers to the SPARQL query after the rewriting of the results. So the time has come for the demo. This is the architecture of the demo, which is about adding semantic search on top of Open Data Hub, a part of Open Data Hub data, the one about accommodations. So the database here, it is specifically the database of Open Data Hub, or a copy we have of it. We have this semantic search API I showed you before, this Swagger API interface. And we have on top, because we are dealing with that in a virtual knowledge graph setting. Okay. So we have different ways of using this architecture. Of course, you have the SPARQL endpoint, where you can send your SPARQL query, and then, as I have shown you before, it will undergo this process, and then you will get your results. Since we are wrapping TAID, for the bad reasons, we are also exposing a port where you can connect via JDBC in order to also issue SQL queries. And then you have the user interface, which is the one I can use here to show you in real time how it works. I hope. Okay. So this is currently public, but the machine is not a strong one. So if you want to try it, be careful. So here is the query that is already prepared, because you can set up a set of predefined queries. And here you see I'm looking for matches to my query, which is about horse riding. And then these matches should be about an entity H, which is a lodging business, which should have a certain name, a description, a certain rating. And then I say the rating must be greater than 3, so I'm looking for 3 stars accommodations. And then here I'm also saying the language should be English, because my query is in English. And this part here is actually for producing a nice string in output. And if I run it, So, you see, I have my results as a table, because the results of SPARQL are a table, but in on top, you can also show them on a map if some of the attributes are geometries, so there is an integration with the so-called GeoSPARQL standard. And here you see I have my top 10 based on the matching on horse riding locations, where I can also have this kind of experience. So if I click here, you see I get the name, blah blah, the ground for children, and horses with the riding ground, whatever. Now, show you that it's not fake. I tried it before with other queries, so here I can also write nice panorama. If I run it, I have a map with the results for nice panorama. If I show you the table, you can also see nice hotel. Well, enjoy the panorama, wonderful view. So in some cases, I mean, the matching is not exact term matching, because there is something more going on in this semantic search. So I can show you, but I won't, because I think I'm using really a lot of time. Sorry. I can show you also the SQL part, but it's exactly the same. I write an SQL query, and what is nice is that I can show you using an SQL client, and when you browse the tables, you will get also a table for the API. So with the schema that has exactly this idea, whatever I mentioned. Okay, now if I can go back. So this mostly concludes this talk. This slide tries to collect the whole, to provide the big picture. So we have multiple sources, relational sources, API sources, which is our focus, but there could be other stuff here. If you ignore the upper part, we can look at them with a unified relational schema. And on this schema, I can write an SQL query, and this SQL query, through an evaluation that needs that use data federation techniques, will be split in subqueries to the different sources. Then, if I also want to add the knowledge graph component, I can create a virtual knowledge graph where I get this knowledge graph view. For doing that, I need the mappings, I need also the ontology, and then I can write a SPARQL query, which will be translated to the SQL query, and then I use the very same machinery as before. Parallel to this, there are the materialization rules that allow me to take data from some tables and put it in some other tables for things that I cannot do online or for instrumental things. Finally, the API bindings are the component that allow me to interpret, to look at the data in some API as a table. Okay, so this is overall picture. Now, some ongoing activities to close this talk. Now, there are many things we may tackle yet. So, first of all, performance. In our group, we are dealing more broadly with data federation and virtual knowledge graphs. We know that the SQL queries that are generated starting from a SPARQL query, these SQL queries, sometimes they are not optimal where they have to be executed by splitting them in subqueries. So we are looking into this. We are trying to find ways where you come up with an optimized ways to generate this kind of queries. So this is a research topic, so still thinking about how to do that. More practical topic, I told you before, for the materialization part, I mentioned change data capture. So in general, we may do a lot to optimize it in order to, and especially to provide some guarantee that if something changes in the source tables, then after a while, let's say I am adding 2 new hotels, after a certain amount of time, let's say 1 day, I will get the data indexed so that I can query it via the API. also in real time possibly, but then we would move more on, let's say, the stream processing using Spark, using Flink, this kind of tools, which is another somehow related direction we are taking in our group. Then all this stuff to implement is quite complex. There are many cases where you can introduce errors. So when I say check all the corner cases, it's because I would not, let's say, certify 100% our prototype. Transactions, they are relevant, especially for the materialization part, in the sense that you would like to have an all or nothing behavior, and we don't have them for the time being, but it's mainly a technical limitation. Usability, here, everything right now is packaged as an extension of OnTop. So in the OnTop repository, there is a branch where you can find all the components, which include the so-called service translator, which is the extension of TAID for calling APIs, and a special JDBC driver that encapsulates, embeds TAID. And then when you connect with this JDBC driver, basically you are starting a TAID, and you have TAID running inside your process. This is the way the approach we used in order to integrate TAID with OnTop. These two components are of general use, so from a packaging point of view, it makes a lot of sense to split them out of this OnTop branch and make them available more in general. Then, of course, we need some tools because really, if you have errors in your API bindings at the time being, good luck fixing them. And we are also working a lot from the application point of view because there are some collaborations and projects where we are dealing with dynamic data. So, for instance, data that comes from the evaluation of predictive models. So, imagine you have your database with some observations, and then you want to run some what-if analysis, where you say, given this input that you enter in your query and the data that you have in the database, what would be, let's say, the increase of temperatures or the decrease in the crop, let's say, production in my area of the world if there is some particular situation tied to climate change. Now, I'm mentioning climate change because the project is on climate change. Another kind, and then we want to do that using these techniques. Another scenario is dealing with the geographical raster data, so data which is a grid of observations, points, whatever. And for that, there are some APIs that you can use to do computations and aggregations. And again, we want one possible way to use them that we are investigating is to access this data through these APIs using the whole machinery that I've told you to do. And that's all. So if there are questions, suggestions, complaints, was not clear.
I think I can speak freely, right?
Yeah, sure.
Now, just I would be interested in the relational part. So, not the on-topic part.
Okay.
Is type right now implemented just as for a data wrapper for Postgres, or is there some server component you also need to start? Does it live inside Postgres, like? For a data wrapper.
What we implemented, you can look at it as a kind of foreign data wrapper, but we are not working inside Postgres.
Okay, so there's a service also.
Exactly. This TAID I mentioned is a kind of mediator that you can put separately on top of Postgres and other sources. And there you plug in your Java component, which is the foreign data wrapper.
So you have to execute extension in Postgres that then talks to this TAID service.
Yes, if you want to do that in Postgres, yes. And then you have to look exactly to how we implement it in Postgres.
And you mentioned robustness. So how much robust would you rate this? Like, could I use it? What happens if the web API gives me a 500? Would it catch it nicely, or would it just explode? And
In this case, there is an all or nothing in our prototype. Also because you see, if some API calls gives you no answer, then who knows what I'm returning as the results of the work.
Okay.
So it's better to
like
fail.
It's a prototype stage.
Yeah, it's a prototype, but I think it's a big issue because if you say to answer this query I need 100 API calls and the 99 are correct and one is wrong, what I do? Okay, maybe given the query I can tell you that your results will be correct but incomplete, and then perfect. But this is something that in the database field they are studying, for instance.
Yeah, it's very interesting to see the semantic web technology is much more used than it used to be 10 or 15 years ago, I guess. It's a comment from my side.
Yeah, well, it's more than 10 years that I want to work on semantic web technology, so of course I agree. Well, I think after knowledge graphs, let's say, where it became an established technology, then there was, let's say, a hype on all of this. So.
And then the question was, how do the semantic web technologies compare a bit to OLAP and MDX? And so this one is a graph-based database model, I guess.
Sorry, how did you compare with?
With OLAP.
OLAP, okay.
And MDX as a query language.
Yeah.
It's a bit of another concept, I guess. It's more about cubes and rotation dice and slicing.
So, in principle, you can take all these scenarios. So, you may still apply what I call the generalized, let's say, OBDA setting. So, imagine you have an OLAP source here, whose native language is no more SQL. Could be SQL with OLAP operators, rollup, cube, whatever. I'm not much familiar with them. Or MDX. Yeah, could be MDX. So you can study this problem and you can apply this framework in order to run it. I'm not aware of specific work to that direction, but I think that's an interesting direction for sure. So yes, it can fit, I would say.
Someone else has something to comment, ask? If not, thank you, Francesco, for presenting us this nice project and this nice technology. And we are really looking forward to see the next steps and maybe a presentation of it at the SFS call or the next year at another Software Developer Thursday. Next Software Developer Thursday will be the 4th of August, and the topic will be temporal data in databases, and the speaker will be Anton Dignes of the University of Bolzano. And now we conclude. Thank you all for being here. It was nice to have you here. Thank you another time, Francesco, for making a nice presentation, and hope to see you next month. Bye-bye.